So the presentation is organized as follows. In the first part, I'm going to give a brief introduction to CERN, LHC, and WLCG, so I will explain all these acronyms. And then I will go into details for the quality part and how we manage quality in the context of the WLCG. There are different aspects of quality that I would like to present: sites, resources, data management, and middleware. And I'm going to focus a little bit more on middleware, which is the area where I work, so I can tell you a little bit more how our approach to quality has been in the last 10 years. And finally, I will summarize the key messages of this presentation. So, well, in case you don't know what CERN means, it's a French acronym. It stands for Centre Européen pour la Recherche Nucléaire. I hope I pronounce it properly. And it was founded in 1954, and it currently has 20 member states. And you can see in this map the countries that belong to these 20 member states. However, CERN is an international collaboration. So we have people from everywhere in the world, physicists that come to do some research. So it's not only people from these 20 member states, it's people from all around the world. It's a real international research center. So for you to have an idea of the people that work at CERN, in 2011, we had 14,000 users. Users refer to these physicists who come from their home institutes, spend some months at CERN performing some research, and go back again to their home institutes. So on average, in 2011, we had around 7,500 people on site. So what CERN does is fundamental research on particle physics, and this means that they try to understand what the universe is made of and how it works. So in order to carry out this fundamental research, what CERN does is to build scientific instruments that are particle accelerators. The latest one, the famous one that appears in the press, is the LHC, which stands for Large Hadron Collider. So accelerators are useful for physicists because they are able to accelerate particles and they smash them against each other, and they analyze what happens after they collide to each other. So normally after the collision of particles, new particles are created, and physicists can investigate what happens there, if there are new particles created, if there's something new they haven't seen before. So in particular, in the case of the LHC, we have 4 places where particles collide. In these 4 places, we have 4 giant detectors called Atlas, CMS, ALICE, and LHCb. And here you have a picture of one of these detectors. This is Atlas. So I don't know if you realize it, but this is a person. So for you to have an idea of the dimensions, they are really like cathedrals. This is how they call them. So the particles collide in the middle of the detector, and all this in the end is a lot of sensors, different layers of sensors that are able to trace what happens after a collision, are able to trace the new particles that are created, where they go, which energy they have, etc. So this is, in the end, what we are going to store. We store digitized summary of all these traces of the particle in the different parts of the detector, and afterwards, physicists are going to analyze these traces and understand what has happened after a collision. And here you have a picture of the LHC. I don't know if you know that the LHC is built underground. It's in a tunnel, 27 meters in kilometers, 100 meters underground. So what is the WLCG? So WLCG is the Worldwide LHC Computing Grid. It's the name of the infrastructure that we are going to use to store and analyze the data produced by the LHC. So for you to have an idea of the amount of data we are talking about, collisions happen 40 million times per second. Not all this information is actually stored. The physicists, with all their experience from previous experiments and previous accelerators, they know where they want to look at for information, so they filter out some of these collisions. In the end, we are talking around 50 petabytes of data every year. This was an initial estimation before the LHC actually started running. Now we have found out that we generate even more data than that. So all this huge amount of data needs to be stored and analyzed somewhere. So the solution that was thought of 10 years ago, when they started to build all this, was grid computing was the technology chosen to do this. So in the end, what WLCG provides is a grid computing infrastructure, which is a set of computing centers connected together through internet, sharing resources, computational resources, and data storage resources. For you to have an idea of the amount of sites, computing centers, and all the machines we have in there, I have put here some figures. So WLCG currently has 157 computing centers in 34 different countries. We have around 200,000 CPUs. Right now, we are able to store 175 petabytes of data. And physicists are able to run around 40 million jobs per month. Jobs are the programs physicists write to analyze the data. And the 4 experiments together, the 4 detectors I mentioned before, have 6,500 physicists. So these are the users of the LHC Computing Grid. And here I have put some pictures. This is a collision of a particle in the Atlas detector. It's one of the dashboards they have. And here you can see one of the control rooms for one of the detectors. And here just a picture of one of the tape robots we have at CERN where we store the data. Okay, so now let's talk about quality and how we manage quality in this infrastructure. So there are different things that we have to take into account when we talk about quality in WLCG. So WLCG needs to be a production quality infrastructure to be able to store this amount of data and have it available for physicists. And this means we need availability, reliability, performance, and manageability as some of the quality requirements. It's an infrastructure that it is used every day of the year. Physicists, they don't rest. They want to find, the Higgs boson and this type of things you can read in the press, and this happens every day of the year. So the infrastructure has to be ready there for them. And then another problem or another issue we have to deal with is the fact that the data for the LHC has to be stored for a very long period of time. Minimum the lifetime of the accelerator, which is calculated to be for around 20 years, but probably we would like to store this data for more time. So WLCG is a dynamic and heterogeneous infrastructure. Why dynamic? So the LHC data is continuously generated. Once the accelerator is running, it continuously generates data. So you cannot miss this data. Things like the Higgs boson, which is this particle physicists want to find, statistically they have calculated that will happen in very rare occasions. So you cannot take the chance of losing the data where maybe the Higgs boson is. So we really have to make sure that once the accelerator is running, we always store the data it produces. Then, if you remember, I mentioned WLCG is made of 150 sites. So this means heterogeneous and distributed computing centers, and we go in this part of the slide. But at the same time, these people, of course, manage their computing centers in many different ways. They have different methodologies, different cultures, different technologies. They have, moreover, to update software and hardware very regularly. There's new technology, new equipment arriving, new versions of the operating system. So it's a very dynamic environment. And then HEP, which means high energy physics, the physicists, they have very changing demands. So during the last 10 years, user requirements coming from them have been very diverse. So we really need to adapt to this changing environment. Heterogeneous, I have already mentioned that we have made of 150 sites distributed all around the world. And actually, WLCG depends on 2 infrastructures that are managed in Europe and in the United States by the OSG and the EGI project. So these projects themselves have also their own ways of managing the grid. They have their own methodologies, and we have to interact with them. So managing quality in this particular context, I think, is very challenging, as you will see in the next slides. So in the next slides, I'm going to talk about quality in terms of sites, resources, data management, and middleware. Before going into detail, I want to mention what we call service and data challenges that were, let's say, like the testing we did to make sure the infrastructure was ready when the accelerator was actually working. This took some years, and actually the grid was ready much before. And thanks to this stress testing, this performance testing, we made sure the infrastructure was ready by the time the accelerator was going to start generating the real data. So here you have some of the dates when these exercises took place. These exercises basically stress test the infrastructure to make sure the data throughput, workloads, service availability, and reliability were met to the conditions that were needed by the time the accelerator was starting, that it was at the end of 2009. I also wanted to show in this slide the different projects that have contributed to WLCG. In particular, these projects were developing the middleware. The middleware is the software that runs in the grid that makes the grid look like a unique computational resource for physicists. Physicists don't know that there are a lot of computers connected together, and this is thanks to the middleware. So WLCG infrastructure goes in hand with this project that helped to develop this middleware. And then, of course, the LCG project itself that designed and implemented this infrastructure. Okay, so let's start talking about the quality of sites. So as I said before, there are 150 sites, and they are organized in a hierarchical model, in a tier model. Tier 0 is CERN, in the center of this hierarchical structure. It is the place where the data from the different detectors arrives first, and it is stored there. There's a permanent copy of the data always at CERN. Then this data is copied in 11 Tier 1 computing centers, and there is dedicated network connections to each of them. These centers are everywhere in the world, in Europe, in America, in Taiwan there is one as well, in Canada. So Tier 1 centers are computing centers, very big ones, which also offer the possibility of storing data on tape. So this is the difference between Tier 1 and Tier 2. Tier 2 is more than 140 sites all around the world again, basically providing computing resources and not necessarily storage resources. So storage is the most important part at the beginning, because we have to make sure we store the data. Once the data is stored, we have time to analyze it. Analyzing the data in particle physics is not critical. I mean, we can take time to do that, but the most important is that we store the data first. So in order to become a WLCG site, what happens is that sites interested in participating in the WLCG collaboration, they sign what it is called a memorandum of understanding. It's a kind of contract. And then there they define pledges, which mean what they promise to provide to the infrastructure in terms of resources. So they define the computing resource levels, including processing capacity, networking, storage, and then service level for the middleware or software related to grid operation services, like monitoring, accounting, user support. So it's a pity, I think this slide you cannot see very well, because the blue dots are the Tier 2 centers, the yellow ones are the Tier 1, but for you to have an idea that it is really a distributed infrastructure. So how do we check the quality of sites? So what metrics do we have? So we have what we call site availability and site reliability, and we have our own definition of these metrics. I have included them here for you to understand how WLCG interpret these terms. So we calculate site availability and site reliability every month. There is a tool to do this. I will talk about it later. And this includes reports about the different availability and reliability of the sites, which are sent to the WLCG management. So they really check that sites are providing the resources and are meeting the service level agreements and so on. How do we calculate these metrics? We have a tool for this. It's called SUM. I will talk about this in the next slide, which basically runs some tests that are considered critical, and then this is defined together with the physicist. And then if the tests are passed in the site, the test in the end tests the services that the site is providing. If these tests are successful, we consider the site is available, is working fine. If they are not, for instance, you can have here some yellow or red, we contact, of course, the site to understand what's happening, what's going on. So sites and resources are very much tied together. So when I talk about quality of sites, it's a little bit of talking about quality of resources, because in the end, a site is a set of resources. So WLCG, as I said before, is running 1.1 million jobs a day, and it has to store a lot of data. In 2011, it actually stored 22 petabytes of data. So monitoring that the infrastructure is working is fundamental to be able to provide this, right? So SAM is the tool I was mentioning before, is the service availability monitoring. It's a tool that it is developed at CERN, and it's based in this technology, so it uses Nagios, messaging, and it has a visualization portal. And it's this tool where we write a series of tests, of probes, and then we run these tests in the different services, in the different resources of the infrastructure, and we monitor the result of these tests, checking whether the services are up and running or not. On top of SAM, there are a lot of tools developed either by physicists or the WLCG operations team. We have, for instance, the grid map tool, which is a visualization tool where you have a square per each of the WLCG site. The bigger the site, the bigger the square. And you can see very quickly the status of the whole infrastructure. So if there's a lot of green, it's good news. If there's some red, then you have to check what happens. Then we have a very nice tool, which I think is pretty nice to show to people to really, so that they can really see that the grid is used. And it's a tool based on Google Earth where you can really see the real activity of the grid in a particular moment. So this is something anyone can download and install. We have an instance of this running in our computing center. It's very nice when there are visits so that they can really see how the grid is being used and how the different jobs are running from one side to another. And then we have a lot of dashboards implemented by the experiments. So not all the experiments uses all the resources of WLCG. Each experiment have agreements with some of the computing centers. So for them, it's very useful to have a tailored dashboard which monitors the resources that are actually important for them. So they use SAM to develop these dashboards. Then we also have accounting to know how the resources are being used. We basically do accounting right now for CPU usage, and we are working now in doing this for storage as well. So what we have now is this accounting portal, which only shows for the moment information about CPU usage, and it basically relies on having sensors in the different computing elements, which are the services where the computing power is. And we have a visualization portal as well where we can have all these graphics and have an idea of how the infrastructure is actually used in terms of CPU. Okay, so now I'm going to talk a little bit how we measure the quality of resources. What metrics do we look at? So one of the metrics that are very important for us is incidents reported by the grid users. WLCG has a tool for this, which is called GGAS, Global Grid User Support. It's a single entry point for all the grid users to report any incident in the infrastructure. And I don't know, but you can imagine this was very hard it was a very good achievement, a very great achievement to convince all the physicists to go and use the same tool, avoid using emails, contacting directly to the developers, the site managers, and so on. After some years, GCAS is really a reality. People are using it, and this is very good to understand what's going on, if there are problems, how much time we need to put the services back into work, get statistics. So it's really a very powerful tool for the operations people. So we have 3 levels of support in GCAS. The first level of support is a rota between the different WLCG sites. So the system administrators are actually looking at the tickets. They are experts. If they don't know how to solve the ticket, or it's a ticket that really is affecting one particular site, we go to the second level support, which is the different specific sites. And finally, the third level support, which are the developers, the middleware developers, or if it's an operations tool, the operations tool developers. So we have a way, normally we don't have support any time of the day. We give support only during working hours. However, if we talk about critical services, we have a way to specify that a ticket is affecting a critical service, and then we raise an alarm ticket. And alarm tickets are taken care of 24/7. So there is a way, we have an organized way of really dealing with these tickets. And then when things are not working as they should because a ticket is taking too long to be solved and is something very, very important, there is a closely follow-up in the daily operations meeting, that it is a meeting where the infrastructure is monitored, where these type of things are discussed to see what's happening, why something is not being fixed, and so on. So here you have some snapshots of the GCAS tool. This is the type of information you have to fill in if you want to submit an alarm ticket. Not everybody is allowed to submit an alarm ticket, only certain expert people who are able to identify that something is really affecting a critical service. Then we generate every month statistics on the time to resolve tickets, the number of incidents per area. So we have infrastructure, middleware, databases, storage, network. This is also something very useful for the management. And then here I just wanted to show you some definition of the different service levels agreements we would like sites to cover. In particular, this is for tier 0. So this is for the services running at CERN. Okay, so I have explained how we deal with quality for sites and resources. A very important area is data management. So as I have mentioned several times, the amount of data is huge. It's more than 15 petabytes per year. This was the number that was used at the beginning when the LHC, before the LHC started working. Now we see it's much more than that. But the nice image we were using to explain what this really means is that if you were putting this in a tower of CDs, it was going up to 20 kilometers of CDs. So imagine now if we have 22 petabytes, it's much more than that. So data, I think I said before, is stored in tape in a permanent way in tier 0 and tier 1s. So there are 2 copies of data. There's a replication of data. So what the WLCG infrastructure needs to provide to make sure we store all this data and we are able to copy this data. So we have to provide networking among tier 0 and tier 1s. And this picture, you can see how the computing center is connected to the different detectors, and then the computing center is connected to the different tier 1s. We have to make sure the necessary data transfer rates required by the different detectors are provided. So in this picture, again, you can see that the different experiments generate data at different, let's say, they generate different amounts of data, different transfer rates, because not all the detectors want to store the same amount of information. Some store more than others. For instance, Atlas is storing more than the others. So we have to make sure these data rates are kept and the information is able to arrive to the computing center as it is generated. And finally, WLCG needs to provide data storage and archive for the LHC data. And here you have a graphic of the data storage at CERN in tape. And as you see, it has grown a lot since the accelerator started working. So what are the type of metrics we look at when we talk about data management? And this is a broad topic where I wanted to talk about networking, data transfers, data storage. So as far as networking is concerned, of course, we have different ways of monitoring the network. So the network for the LHC is called LHC Open, is the optical network. And here you have a map where you see the different connections with the different tier 1s. We have dedicated 10 gigabit network links. And then we have, of course, monitoring tools to make sure these links are working and are fine, and otherwise we react. We have a way of managing incidents and so on. We also have dashboards to monitor the transfers between the different detectors and CERN. And for this, we have a middleware service called FTS, File Transfer Service. So looking at FTS, we are able to see the different transfer rates from the detectors to the CERN Computing Center. This is also very important to check that everything is working as expected. In terms of data storage, we also have ways of monitoring what's going on with the tapes, with the different tier 0 and tier 1s storage systems. So as I said before, we have distributed data storage. There's not only one copy of data at CERN. We make sure that at least there is a copy at least in another tier 1, so data is replicated. Once you copy data on tape, is not finished, the job is not finished, let's say, because what they are doing is that they are continuously migrating data to newer media. So as soon as there are newer tapes in the market, which are bigger, then they move to those tapes, and like this, they are also able to store more and more data using the same robots, let's say. So they move to new tape. And then, as I said before, data is, of course, replicated. This is very important because when physicists run their programs, it's very important that they do not need to access only CERN. So data is distributed everywhere, and this helps to access it faster and in a more reliable way. Then I wanted to show here something. When I talk about data, and I'm always saying that the data coming from the detectors and so on, this is what physicists call raw data. It's the data that the detectors have read, the electronic signals that they have registered, but this is not the only type of data that it is stored. Physicists do simulation, and simulation is something very important for them, and they also store this data. It's also a very big amount of data. Once the raw data arrives, they do what they call event reprocessing, and then they store this reprocessed data, and then the analysis data, they also store it. So in the end, they are storing a different, based on the same data, they are storing different processings of this data. So it's not only the data that comes from the detector, there are other things that need to be stored as well. And here in this snapshot, you can see one of the monitoring systems we have at CERN to control the status of the different storage systems at CERN and in the different tier 1. Okay, so I'm going to talk now a little bit about how we manage quality in the middleware. So as I said before, the middleware is the software that it is running on the grid. It's made of very different types of services that are developed by different development teams, basically belonging to different projects like EMI and Open Science Grid. This is an American project, this is an European project. So these are the middleware providers that develop middleware for WLCG. We are talking about distributed development teams again, small development teams all around the world. And we have, of course, distributed testbeds. This is very important to be able to test the middleware. Basically, testing starts internally in the development team. So they write their own test plans. Once they do the testing, they provide test reports. And then we, of course, have a stage rollout testing. It is very difficult to recreate the production conditions of this type of infrastructure in a testbed. So through the years, and I will talk about this a little bit later, we have realized testing in production is very, very important to improve the middleware and make sure it actually works in production conditions. So stage rollout is really a very important stage before moving to the production infrastructure. Then we have a way to test new features when there is a new service that we want to deploy or a very important feature we want to introduce in an existing service. We use what we call pilot services. So this is a collaboration with a particular production site that deploys this service and allows us to test it in production conditions. And then if we are happy, we deploy it and we roll out in the usual way. I also wanted to mention that as far as middleware is concerned, we have now common quality assurance policies. This is very important because, as I said before, we are also talking about an heterogeneous environment of many different development teams who have their own ways of working, their own cultures, their own methodologies, and it was very important to be able to have an homogeneous layer of how we wanted the middleware to be released. So we wrote these quality assurance policies, which basically are giving guidelines for building, for packaging, for documentation, for testing. So we make sure that when a developer wants to put a new release out, it has followed these quality assurance policies. And then thanks to the fact that we have this homogeneous layer, we are able to generate metrics for the middleware, because otherwise imagine how you would be able to interact with different change management systems, different testing frameworks. It would be impossible. So thanks to the fact that we have these common policies, we are able to build some automated tools that allows us to calculate some metrics for the middleware. And here, for example, you can see the number of changes in the different quarters for the EMI project for all the products. So this is really, really useful for a project like EMI to be able to have this picture of the status of the changes in the middleware, in the EMI middleware. So what type of metrics we are calculating for the middleware? So again, a very important metric is incidents once more. So if you remember, I mentioned that GGAS, the tool we use for incident management, had 3 levels of support, and the 3rd level of support is the middleware experts, the developers. So we are able to generate this type of diagrams showing the number of incidents or the time it took to fix a certain incident and so on. So this is, of course, followed up by the release manager, the person who is coordinating the release process, to follow up with developers when a ticket is open for a long time and so on. Then another important thing is that we have a way to track requirements coming from WLCG. So the EMI project in particular has a tool where we track all the requirements coming from the physicists to make sure they are implemented in the middleware. So out of this, we are also able to generate some metrics. No? After a release, we can say how many user requirements have been addressed, how many are still open, and so on. And then we also have people working in security. Security is something very important for the middleware. So it's very important that users are able to access the infrastructure in a secure way, and there has to be a high level of security in the services. So we have a group of people looking at possible vulnerability issues, and when they find one, they emit a report, and then we react on it, and we fix it, and we follow the recommendations they give. So we are able also to generate some metrics related to security. Okay, so now I'm going to explain a little bit how the approach to quality has evolved in the last years, since the beginning of the projects that were developing middleware. So in the first years, software was of course not very mature. It was not yet very clear what the physicists wanted. So at that time, the main focus was on testbeds, how we wanted to organize the testing activity, what type of testbeds we wanted to provide. We needed something allowing these distributed groups of developers to be able to use a testbed and connect to it, connect its service to a testbed, and be able to interact with the rest of the middleware services and check that everything was going fine. So most of the effort was put in the early years to develop testbed. And here you have a diagram where you have a testbed at CERN, and the different developer teams are able to connect to it. A lot of testing was done manually at that time. There was very, very little or no automation at all. And the testing was done centrally by CERN. So developers went developing, and then testing was actually done at CERN in a central way. Later on, software became more stable. It's the natural evolution, but use cases from the physicists and from the way the infrastructure was actually being used became more complex as well. And we also had very diverse deployment scenarios. This means that we had big sites having their own fabric management system that had to somehow interact with the way middleware services were installed. We had small sites that didn't have much time to understand the different ways of installing the different middleware services, so we had to provide a way for them to do this in an easy way. So this made the whole thing a little bit complex, because you had to address very different type of users from the site perspective. In that years, we focused on test automation. It was a long time. Now we have a high level of automation. I will mention it afterwards. But at those years, we really focused on automating tests to make the time to production shorter, because there were a lot of complaints that it was taking a long time to release a change in the production infrastructure, and this was mainly due to the fact that we were doing manual tests. And then what we realized those years is that we were doing a lot of testing, but then when it was going to production, it was failing. So we realized we really need to move testing to the production infrastructure to be able to test under production conditions. And here it was the beginning of the stage rollout. You have here a diagram explaining a little bit how the stage rollout works. Basically, we have a set of volunteer sites, the WLCG sites that volunteer for installing a new version of the middleware as soon as it is released. And then once this is correct and they are happy with it, they've been running it for a while, they give the green light so we can deploy it in the whole infrastructure. So in case something goes wrong, the rollout, it's not impacting all the sites, but only a few of them, and it gives us really information that everything is working in production circumstances. Okay, so where we are now with quality and the middleware. So software now is mature. We still have complex use cases, But now we have a high level of automation. All the effort put in the last years, I think, has paid off, and now we really have a lot of test automation. Moreover, we are now making development teams to really look at these quality assurance policies, so we make sure that what we deploy in the infrastructure is it meets the quality criteria we have defined, and this is very important. And here in these diagrams, you can see the different type of tests the development team does, and how for the different updates of the EMI middleware, they have really reduced the number of no's, saying that they were not doing any of these tests at all. So with the policies we really have enforced, and we really have helped to improve the testing performed by the development teams. And then we have focused a lot in stage rollout. So now really stage rollout is a fundamental step before really moving something to production. We are really making sure the middleware is working in production conditions. How we see the future? We still think we need to continue automating our tests. There are still tests that are not automated. It is true, it's a complex environment. It's not always possible to automate everything, but we still think we have to put effort on this area. And we really want to have an organized and structured stage rollout. It's the basis for us for real testing. So we really hope we can take into account all the different combinations, because we have a complex environment. We have, in many cases, different versions of operating system. The configurations of the sites are very different one from each other. So it's a complex environment, but we really think we have to put effort on a stage rollout, because in the end, it's what it really tells us if something is ready or not. And then, of course, continue the cooperation with production sites. It goes together with what I was mentioning about organizing a strong stage rollout. Okay, so I have covered all the topics, and I just wanted to summarize what I think are the key messages of this presentation. So we have a distributed infrastructure. This is a reality. It's there, and it's been working for several years. And we really have to take into account that quality has played a very important role to provide this infrastructure for the physicists. So we really need to look into quality and give it the importance it has to have something like this. Then, in a complex environment like the one I have presented, it's very important to have automated tools. It would not be possible to monitor something like this if we wouldn't have things like SAM and all the different tools I have presented. WLCG is a lot of things. It's sites, it's resources, it's data management, it's middleware, and we really need to look into the quality of each of these different elements. And finally, this is a changing environment, it's evolving, and of course we always need to be looking at this change and make sure quality is also evolving and adapting to the different needs. And this is all for me.